This is Physics 2211, Lab 2 Constant Velocity. So, the purpose of this lab is to compare the observed motion of an object falling after it is dropped from some initial height to two computational models, one with drag and one without drag. Our object in this case is going to be a paper ball, while the observed position we'll get using the track graph. The predicted position we'll get using glow script code. So, this lab will aim to demonstrate Newton's second law and the effects of drag force. So, our principles. Well, Newton's second law states that net external force equals change in momentum of a system over time, which is this here. Now, we can use this to derive the velocity update formula, which we're going to use alongside the position update formula. Note in this case that F net is Fg plus Fd when we're considering Fd, and we can see the definitions for these two up here, the formulas. And gravitational force is an attractive force that pulls objects with mass towards each other, while drag force is a resistive force that opposes the motion of an object as it's moving through a fluid. So let's see our setup for the experiment. So our system is going to be the paper ball, the surroundings will be everything but the paper ball, and our assumption is going to be that the ball moves only in x and y directions, not towards or away from the camera, and the ball will be dropped from some initial height with no starting velocity. So our initial condition is time equals 0 and position is around 1, and our computer model will be generated using GlowScript. So you can see the preview. We can see that the position tracker, which accounts for drag alongside gravitational, is most similar to the tracker app, whereas the one that does not take drag into effect, you can see a gap open up, it's not. So our procedure is going to be to record a video of a ball falling from an initial height, then use a software tracker to determine the ball's position frame by frame at set time periods, and 3, use GlowScript to create a computational model of the ball's predicted motion with and without drag force using the starter code given, and then use Excel to compare the actual motion and predicted motion in a position versus time graph, and then we're going to make appropriate conclusions from such. So in our tracker video, we can derive our initial position and then our initial velocity, which we will later use in our GlowScript code. And this is how it looked, the position versus time graph for just our observed position in the tracker. So our computational model during GlowScript. So here we set a mass of the ball that we found by weighing it. We have our initial position, initial velocity, and then our value of g. And then for the one without drag, where b is equal to 0 because we're disregarding it, and our f net is just f grab. And then we use velocity and position update formula. Now, as for with drag, we're going to set b to a value of 0.005, and in this case, f net is not just going to be f grab, but it's going to be f grab plus w, which represents the force from the drag. Now, for our computational output, we can see that with no drag, we just have two arrows. This represents f grab, this the velocity. Same thing here, except we also have an orange arrow representing f drag. So when we actually plot our results, this is what we can see. We can see that when we accounted for just gravity with no drag, we can see that the position changed slower with time. It decreased at a slower rate, and a gap opened up here. Well, while when we accounted with drag, it was more closely aligned with the observed motion. And this is because in real life, like with the observed motion, there is a drag force. So in our computational model, when we accounted for drag force, well, now it's become a lot more in line with what we would actually see. So now we can talk about some errors. One, we could have been tracking at an angle, which would have distorted the position it's traveled within a frame. 2, we could have had rounding errors in calculations. 3, human error. Or 4, and probably most importantly, alongside with 5, is that our F net might have not just been F grab plus F drag, but we could have had additional external forces from, I don't know, someone coughing or the air conditioning more probably. And 5 is our ball shape, because it was a paper ball, might not have been perfectly symmetrical and round. So to talk about which model predicts a terminal velocity. Well, the model with only gravitational forces shows a velocity that is linearly increasing, while the model with gravitational and drag forces shows a nonlinear growth in velocity, which plateaus over time, thus predicting a terminal velocity. And when I mean linearly increasing, I mean linearly increasing in the negative direction, because obviously it's falling downwards. Now, what if the object was thrown directly upwards? Well, there'd be no change because terminal velocity is based on when the magnitude of the drag force is equal to the magnitude of gravitational force. Terminal velocity is reached more quickly, however.